We are the Signal Integrity Group. My name is Logan and I'm working with Edward and Ahmed. And the objective of our lab is to use a shift register and a microcontroller to transmit data. And then we're going to compare that data and send it through parasitics using capacitors and inductors. Using the data and the circuit we created, we're going to create an eye diagram and calculate the bit error rate. And then at the end, we're going to discuss a recovery method to try to reverse all the parasitic effects.
Let's say you want to send a signal from A to B. And this is just some message from me to Ahmed. Come here. Alright, he's there. Alright, cool. Alright, so here's me, there's Ahmed, and ideally the message just goes straight to him. But ideally, or in reality, what actually happens is rather than coming through and just being ones and zeros, it kind of turns into something else like this towards the end, where it's not really ones and zeros. It's ones and zeros, but they're not actually clean blocks. They're these little bits, and that's caused by the capacitance and the inductance of the wire. And depending on what you're doing, this might just be going from one chip on your motherboard in your computer to another chip on the motherboard in the computer, or it might be going from Swearingen to 300 Main, or it might be going to the next town over. Depending on the situation, depending on the kind of wires you're using and the frequency of the data you're trying to send, the parasitic elements of the wire are going to affect the data signal more ideally.
So the idea of our lab was to have a transmitter and a receiver working in conjunction to transmit to the receiver a data input that we define to begin with, and ideally it will go across an ideal line and it will have no distortion in the signal because there's no impedances, no components in the ideal line, and we will get out what we get in. In a non-ideal line and in the real world, you'll have varying impedances due to capacitors and inductors working together that will distort the signal. So in our circuit, we have a series RLC circuit working in the non-ideal line, and we're going to measure across the capacitor in order to see how the signal gets distorted. So for our transmitter, we're going to have a microcontroller, and it's going to send the signal to the data as well as the clock. And this is why the shift register is called a serial in, parallel out, because we have a serial data coming in, and it outputs it outwards in a parallel fashion through these 8 bits, and each one will go to an LED, and the LED will light up depending on whether it's a 1 or a 0. So to look at the equations, so for the transfer function of this RLC circuit, it's generalized by 1 over S squared LC plus SRC plus 1, and to solve for the center frequency, or also known as the resonant frequency, it's 1 over the square root of LC, and to solve for Q, which is the quality factor, it's 1 over omega naught RC, where omega naught stands for the center frequency. Q typically depicts how much a signal will ring over time as it's transmitted. So you might see it like bottom out, but as it bottoms out and it reaches 0, it'll go past 0 and it'll curve back up and go back to 0. So since we solve for W naught and Q, we can sub it back into the generalized transfer function, and we can have 1 over S divided by W naught squared plus S over Q W naught plus 1. So now to get to how we're going to measure and analyze our signals. We're going to be measuring across the capacitor using an oscilloscope in persistence mode. When an oscilloscope is in persistence mode, it basically eliminates time, and it doesn't measure in any intervals. It measures across all time, and it keeps it on the oscope, and it never erases. That way, on the oscope, you'll see an eye diagram that will look something like this, because it resembles an eye. So you can think about it that instead of measuring across an interval of time, it'll be 1 unit interval in which bits are measured and triggered over time based on the clock signal. So over here you have the amplitude, which you can think of as 1 or a 0, as it triggers from the top to the bottom. So if it goes from the top to the bottom, it'll shift from a 1 to a 0, and depending on the clock it will read either a 1 or a 0 depending on where it is read in reference to a voltage. So there could be a reference voltage here, and if it reads exactly at that time, it will read as a 1 as long as it's above that reference voltage. And it will read as a 0 depending on if it's below that reference voltage. So that is how bit errors can occur, or like errors in a signal can occur. If you were to read, say, over here, then your bit is supposed to be read here. Well, it's supposed to be read as a 1, but since it's measuring over here, it's below the reference voltage, and it will read as a 0, and it's supposed to be read as a 1. Now we want to talk about the ideal cases of a eye diagram, and what we will see typically in the real world in a good scenario, and what we'll see in a really bad scenario when we're looking at eye diagrams. Typically, ideally, rather, you see that it transitions from a 1 bit to a 0 instantaneously. Now, this isn't, you don't see this in the real world because nothing is going to happen instantaneously over time. What you'll typically see is something like this, where it takes an amount of time as it curves down to transition to a 0, or an off state. Now, there's also a worst case scenario for this, and this will depend on the components that we have and their parasiticness from the capacitors and the inductors. If you have a low dampening ratio, you're going to have a high ringing that you'll see as the eye diagram starts to like curve. You see it like right there, and you see it here, and you see it in various other parts. Also, what you'll see from a low Q and a high parasitic amount in your signal, you'll see that the width of the window, of the eye window, you'll see that it's like small, or you'll see that the signal's window height is like small and it shrinks. And if you can compare it to this one over here, where you have a real world best case scenario, you have a high amplitude, a high window height, and you have a pretty good wide window width. And what this causes is the transition time. So like, if you think about it now in terms of time, it takes a low amount of time for it to go from here, right? Low amount of time to reach a 1. So that's known as the eye crossing percentage. The lower the eye crossing percentage is, the faster it transitions from a 0 to a 1. And that's what you want in a eye diagram that you've made from a circuit. If the circuit's good, you'll produce a good eye diagram. If you have a lot of parasitic values, you'll produce a bad or worst case eye diagram. In the worst case scenario, you will see later on in some of our results that it will become a mess of garbage like this due to the high parasitic values in the capacitors and in the inductors. So those aren't really good or useful eye diagrams to try and analyze. So I talked a lot about a Q, a variable called Q. This is known as the quality factor. So if you consider a step response over time, if you have no dampening, it's just going to oscillate. And eventually it's going to die out and you'll see it converge to 0. But if you add a little bit of dampening, let's say the dampening ratio is 1, you're going to see it step down really quickly, not as fast as 0, but it'll step down and it'll converge back to 0. And it'll ring above, or below rather, it's going to ring below 0, but it's going to go back to 0. If you increase the dampening, the step response takes longer, but you don't see it ring anymore. So dampening helps eliminate Q, but it makes the response take longer to get to 0. And again, as a comparison, if you make the dampening 5, it takes even longer, but the signal is steadier.
This is the experimental setup we came up with. Right here we have an mbed microcontroller. We have a serial in, parallel out shift register, and we have 16 LEDs. We have 8 LEDs over here that represent an ideal signal coming from the microcontroller, and then these 8 LEDs are representing the signal that is coming out of the shift register. In an ideal situation, both of these LEDs, these pairs of LEDs, will be the same. So right now, as we have it running through our filter, the data line is being corrupted by the parasitics that are created in these elements right here. And we see that we have some LEDs that do not match these LEDs. So we have a bit error that we can calculate. If we go back to an ideal situation, and we move these wires to where they go straight from the microcontroller into the shift register, we see that now the LEDs are the same. And this is what we're aiming for. Whenever we send a wire over a great distance, we want it to be, or even over a short distance at a high frequency, we want the data to be reliable. In our first screenshot, you'll notice we have an ideal line right now that is not being deteriorated with any parasitics quite yet. Zooming in, you can see that it's actually very ideal right now. The wires are very short. We add an inductor, and you can see how an inductor causes the circuit to ring a little bit more. And now, as we go through these screenshots, notice how as we change the capacitive, inductive, and resistive elements, the bit error rate changes. And the eye diagram, as you can see, is drastically changing with that. All right, our conclusion. Am I starting? Sorry, I didn't think we realized to establish this.
What was the first thing? Oh, the problems.
All right, the problems we had at the experiment. Initially, when we first made this, we had one transmitter and one receiver little embed unit. And the problem is that the embed bootloader actually bogs down the chip a decent amount. And so when we wanted to have a clock signal generated and a data signal, we had to run those two lines of code at the same time. We couldn't just declare a clock signal and a serial out signal. The embed didn't really want to work that way. So we had to create our own clock signal and our own data signal to output. And that actually slowed it down. We couldn't get the speed above about 215 kilohertz, if I remember. Receiver has to be able to read the clock signal and the data signal and interpret that data very fast. And the math to do that inside of the embed was actually too much for it to be able to read the clock signal and do all the data. So we actually were not able to use the receiver unit unless we were going to slow down the transmit unit. So for the sake of the experiment, we ended up just using the shift register, which ended up being much faster. The shift register can actually operate at a very high frequency. And so we didn't have any problem with the shift register. It probably would have looked a little bit better, and we would have been able to maybe quantify our results easier if we had the receiver unit, but ultimately this design that we chose ended up working out really well for us.
So after we finished our experiment with the shift register, we did some research on the recovery method and found the pre-distortion method.
One of the things we wanted to talk about were recovery methods. So one of the things you can do to your signal is pre-distort it. Because the distortion comes after it goes through the entire line, we pre-distort the signal. That way, after it goes through the line and gets all the distortions, it's actually distorted into what it's supposed to be. So like an ideal line, we have our ones and zeros, and they're nice, squared off at the leading and the falling edge. In reality, over any wire usually, as you go longer in distance, you start having more distortions, and the signal is less recognizable. But when you pre-distort and you put the distortions on it, as it comes to the end, it actually starts to resemble more of what the waveform you want to actually be. So when you use pre-distortion, you can actually recover from the errors you would receive in your line. And you see this system in a lot of devices, like if you buy an active HDMI cable or some sort of system that lets you use a USB printer over a long distance. Like things that normally you can't go more than a couple feet with. You'll generally see they'll add active devices to compensate for the parasitic elements of a wire.
So what did we learn? We learned how to analyze a signal as it passes through a filter, simulating what would happen in the real world as signals are transmitted really quickly. We've learned how to interpret eye diagrams. We've learned what Q means. I know personally I didn't really quite understand what it meant to have a Q when Dr. Bryce was going over it. If anything that we would do differently might include having two faster microcontrollers so that we wouldn't have issues on the receiving end. We would also maybe then be able to analyze the error in the bits over real time instead of having to look at the LEDs, and we would also be more precise since dividing the bits over 8 LEDs means that we can only measure the bit error rate in increments of 12.5%
Having a C++ guru.
that would have been great.
That would have been really useful.
We had to find headers for to drive our transmitter, and we didn't even really understand what was going on.
So we did learn a lot about C++ in the process.
Definitely.
Unfortunately.
Definitely. But yeah, that about sums up what we learned, and I've hit what we would do differently. I think that's a wrap. Hope you liked our Hawaiian shirts.
Mr. Metz.
This is for you.